Okay, so good evening. Uh, so today we are going to discuss about matrix factorization, the discussion which we were having before your mid-sem recess. So what is matrix factorization? Uh, okay. Matrix factorization basically means you have data matrix and you decompose it into uh, something useful or into two matrices which multiply mutually and you get something useful. I'll just write a general form. So basically you have, let's say, a matrix V, you decompose it into W and H, and so in order to compress your data, it could be used for various purposes. One purpose could be to compress your data, like PCA. Another purpose could be to find useful information or structure in your data, like in, like in. Can you give me some example of matrix factorization where you want to extract some useful structure from the data? An example of matrix factorization where you want to extract some useful structure from the data. I gave an example that PCA is for data compression, that your data gets compressed to smaller dimensionality representation. An example where you see structure in your data with the help of matrix factorization. Okay. Huh? Which one? Image? Yeah. It could be anything. Image or speech, text, anything. Oh, I have to remind you of so many things. One is k-means clustering. What is that called in terms of matrix factorization? Vector quantization. Right? You have your data, you find clusters, and you map each value in that cluster to the centroid. You represent the data with the centroids only. That was vector quantization. You quantize your data to certain centroids. And then we saw uh, non-negative matrix factorization to find structure in the data, right? The good quality of non-negative matrix factorization is that each of those dictionary elements or those peculiar points, they are interpretable because they are all non-negative, right? They represent different parts in the representation. Let's say in an image, different parts of the image. If it is spectrum, different parts of the spectrum. If it is text, different parts of the text. Right? Okay. So that was just a recap. Now here we have non-negative matrix factorization, which we were discussing in the last class. Non-negative matrix factorization basically means when, okay, I will show it here. When you want to decompose your your matrix V into W and H, where both W and H are non-negative, as well as V is non-negative. What is the meaning of non-negative? Non-negative means it is not negative, or it could be 0 or positive, right? So this is what. It could be 0 or positive, but it cannot be negative. And then when you see your parts, these are your parts. Okay. So what is V here? So okay, V is not just one image. V could be V is a stack of many images, and each image is represented as a vector, right? And that is your nmf. Okay, so this was the paper which kind of introduced nmf, and after this paper was published in Nature in 1999, this method became very popular for various reasons: ease of implementation, interpretability, reconstructability, so many things. Okay, so this is just a recap from previous class. What did we see? So we saw this, we discussed this in detail in the last class. Go through the notes and you will get it, but we will have a small recap now. So we saw one method of NMF, one kind of NMF, it is called PLCA. What is the full form? Probabilistic latent component analysis. Why? Because it has probabilistic interpretations. What is the meaning of that? It means each of your dictionary vector is a PDF. And similarly, each of your activations vector is a PDF, right? So you're working with PDFs. That is why it is called probabilistic latent component analysis. Why it is latent? Because we are doing a latent variable decomposition. Like we discussed about discrete latent variables, continuous latent variables. So this it makes use of latent variables. That is why it is called latent component analysis. Okay. So just to remind, VFT is a data matrix where F means the different data points. Okay. Actually T means the different data points. F means the different elements of the same data point. Means the different elements of the data vector, right? So PTF, this is the original data histogram, which is a distribution PDF, which is being decomposed in terms of the latent variable Z, and this latent variable Z links with different, or it corresponds to different underlying representations, which are non-negative, so interpretable. Like in this case, they are like eyes and nose and ears and different kinds of eyes, different kinds of nose, different kinds of ears, those kind of stuff, right? Okay. So now my F may denote pixel position. So T denotes different samples, right? Different vectors, data vectors. And within each data vector, we have pixels, right? So F may denote pixel positions. And if it is audio spectra, then F may denote different frequency bins. And P, T, F will represent energy in different frequency bins, right? Similarly, in images, what is PTF? PF represents the grayscale value between 0 to 1, right? When it is 1, it is larger value is denoted by PTF close to 1. Okay. Okay. I think the point is clear. Then we have got this representation, but how do we optimize? How do we find the optimal values of PF given Z and PTZ, right? These are our matrices. PF given Z corresponds to W. This is the W, and this is the H, and this is my V, right? So this is the matrix decomposition problem. Now, how do we find out the values of Z? You have been seeing in the past what is the most popular method which we have used for latent variable optimization? EM algorithm. And what is EM algorithm? EM algorithm basically converts sum into products, because you know log of summation is not decomposable, but log of sum is not decomposable, but log of products can be written as sum over logs. So when you take derivative, it becomes very nice analytical form which you can solve analytically, right? So this was the goal. So you see the log likelihood is given by log of PTF, which contains summation inside the log. So we use EM algorithm to take out the summation outside the log. How do we do that? We formulate an auxiliary function L, where we multiply and divide by Q, T, Z given F. The purpose is, okay, Q, T, Z given F is probability distribution, non-negative, and we use, what do we use to formulate this L? What is the, okay, we are optimizing L, and we are assured that this is optimizing our original likelihood function. Huh? Somebody said the answer. Louder. Yes, Jensen's inequality. So, if you remember properly, so we had this inequality in place. So, let us say this is my, I want to maximize my likelihood, right? Okay. So, likelihood is some kind of function, and you want to reach the maxima, which is, let's say, here. But you initialize with an arbitrary value, and let us say it lies here. Okay. Keep in mind that this is only applicable for convex optimization, means it should not have so many maxima. You want to reach the local maximum, not the global maximum, right? Because this method is only, it will take you to the local maximum, not to the global maximum. And what do? You formulate an auxiliary function, let's say an auxiliary function, such that its value is this at this given, let's say at a given Wt. But if you, now this function is always less than your original function. This was your log of sum, and this function is your auxiliary function L. And if you maximize your L, you are assured that you are doing better on log of sum, right? This was the idea of Jensen's inequality and the basic principle of EM algorithm. This is just a reminder. I'm not telling anything new. It's all has been discussed, right? If you have questions, feel free to raise hand. No problem. I can go over it once again. And when you do this derivation, basically you find the Wt like this one, and then from here you optimize on G, which is analytically solvable. You find this analytical solution, and then you formulate another auxiliary loss function at this Wt plus 1, and you reach here. Okay, you reach here, and from here you again formulate an auxiliary loss function and again optimize in this way. Iteratively you reach the local maximum. Okay, so you are iterating between E and M steps. Basically, E step means where you find your QTF so that you shift in vertical direction, means you move your auxiliary loss function up, and M step is where you are actually optimizing over the auxiliary loss function, right? You are optimizing the parameters for a given auxiliary loss function. Okay, today we are going to discuss again NMF, but a different approach. Why I chose this approach? First of all, okay, this is by the same authors, Lee and Seung, who have written the first Nature paper on NMF. In this paper, in NIPS, so they have published two algorithms to optimize your NMF parameters, right? And these are very interesting mainly for the reason that they do not use EM algorithm, but they use the basic principle of EM algorithm. What is the basic principle of EM algorithm? You have a loss function which is difficult to optimize analytically. From that loss function, you construct an auxiliary loss function, an auxiliary function, which you optimize using which can be optimized analytically. So you make use of it. And the property is that it is always less than or greater than. If you are minimizing, then it is greater than. If you are maximizing, it is less than the original loss function, right? So that is the principle. So it is more general than, it makes use of principle which is more general than EM algorithm. EM algorithm is dependent on Jensen's inequality, which means you have to have log and everything in place. But this one makes use of something else. Okay. So what are we going to do now? We are going to go through this paper. So this will be an experience for you. This will be an experience that how you can read papers because it is important because these days things are changing so fast. A few papers like this, they stay for a long time, but most of the papers, they get outdated very easily. Papers before 2012 hardly anybody reads because after 2012 what came in? Deep learning came in. Okay. So similarly, now also the things are evolving so fast. It's very important that you learn to read papers. So I have chosen this paper. It's a very nice paper and very relevant to what we are doing. Okay. So let's see. Let's read the abstract first. Let us. I am also assuming. Okay, I am also reading it for the first time. A non-negative matrix factorization has previously been shown to be useful decomposition for multivariate data. Okay, so they have shown in the, if you read the Nature paper, it was shown. Two different multiplicative algorithms for NMF are analyzed. Now they are proposing two algorithms for optimizing NMF. They differ only slightly, fine. The algorithm can be shown to minimize the conventional least squares error while the other minimizes the generalized scale divergence. So two algorithms are shown. One is minimizing least square error, which you all have mastered already, right? And the other is scale divergence, which you also have mastered. So that's why this paper is very relevant. But the approach which they use is very different and it's very impressive. The monotonic convergence of both algorithms can be proven using an auxiliary function analogous to that used for proving convergence of EM algorithm. So there you go. So they are making use of an auxiliary loss function. They are constructing not using Jensen's inequality, or maybe in one case yes, but in other case no. But the principle is maintained that we are constructing an auxiliary loss function. The algorithms can also be interpreted as diagonally rescaled gradient descent, where the rescaling factor is optimally chosen to ensure convergence. Okay, this part can be ignored for now. Okay, let's read the paper now, the main text. Unsupervised learning algorithms such as principal component analysis and vector quantization can be understood as factorizing a data matrix subject to different constraints. We all saw that, right? All the approaches which we are discussing, including starting from k-means, then PCA, and then what did we see then? NMF. So all these approaches basically do not consider the labels, right? They just look at the data and they do some decomposition. So that is why they are unsupervised approaches, right? Not supervised. Supervised means you have labels with you and you make use of them. Okay. Now, depending upon the constraints utilized, the resulting factors can be shown to have very different representational properties. PCA, okay, now they are comparing these different methods. We have already done it in our previous class. We compared PCA with VQ or vector quantization and with NMF, right? So this is the same thing. We can ignore, we can skip this part. We have previously shown that non-negativity is a useful constraint for matrix factorization that can learn a part's representation of the data. The non-negative basis vectors that are learned are used in distributed yet still sparse combinations to generate expressiveness in reconstructions. In this submission, we analyze in detail two numerical algorithms for learning the optimal non-negative vectors from the data. Okay, so basically they are saying that this NMF representation is useful to find the parts, and then they are proposing two algorithms for NMF factorization, non-negative matrix factorization. Okay, so they start with the definition of NMF. So what is NMF? NMF basically means your V is, you want to approximate V. V is given to you, the data is given to you. You want to decompose it into two matrices, W and H, which are both non-negative, right? Okay. Now they are giving some nice things about NMF. NMF can be applied to the statistical analysis of multivariate data in the following manner. Given a set of, okay, now they are, this is very important, right? I will tell you why this is very important. They are saying that given a set of multivariate n-dimensional data vectors, the vectors are placed in the columns of n cross m matrix V, where m is the number of examples in the data set, like we have T and F, so T was the samples, and n denotes the different, it's the n-dimensional basically data vector. So remember, okay, maybe I should write it down. Okay, so what is the thing? One is, what is the representation? So you have vectors. Data is represented as vectors. Each data point is a single vector. Please keep this in mind. Even if you're doing images, you flatten your matrix and form a vector. If it is three-dimensional image or two-dimensional image, just flatten it and formulate a vector, right? So do not leave it as a matrix. Okay, this is important. And how you choose your vectors, this is also important. These are the vectors where you expect to find some structure. I'll give you an example. So all of you have recorded some audio files, right? In the last assignment or ongoing assignment, unfortunately. So you have recorded some audio files. Now just consider each audio file as a vector. Can you do that? If you consider each audio file as your vector, as your data vector, can you do that? Maybe yes, but what kind of structure will you find there? Periodicity or time shift? So very complicated. So it's not a good idea to use that as a vector. So if you transform it into something useful, that can be a better representation as a vector, right? Okay. So we'll discuss this point more as we do more assignments. Okay. So this is important that the vectors are placed in columns, and this matrix is then approximately factorized into an n cross r matrix W and r cross m matrix H, right? This is clear, W and H, where the limiting bottleneck is R, so you are extracting only R components. Usually R is chosen to be smaller than N or M, so that W and H are smaller than the original matrix V. This results in a compressed version of the original data matrix. So you are also achieving data compression, right? So what is the significance of the approximation in equation 1? It can be rewritten column by column as V approximately equal to WH, where V and H are corresponding columns of V and H. In other words, each data vector V is approximated by a linear combination of the columns of W weighted by the components of H. Therefore, W can be regarded as a basis that is optimized for linear approximation of the data in V. Okay, so I have a question now. In PCA, what was your W? In PCA, what was your W? You represent your data in terms of what kind of vectors? Eigenvectors. So W was eigenvectors. But in this case, these are not eigenvectors, these are some non-negative representation. We call it as a dictionary. Okay, dictionary. Why dictionary? Because this is the this is what you carry with you, and to construct different images or different data, you just take a weighted sum of them, right? You can call it a basis or a dictionary, whatever you like. Okay, so this is about W. So W is the basis or the dictionary that is containing the basic building blocks of your whatever data you want to construct. Since relatively few basis vectors are used to represent many data vectors, good approximation can only be achieved if the basis vector discovers structure that is latent in the data. Okay, this is very important. So what kind of basis do you want? It should be able to discover some structure. Why? Because if you discover the structure, then you can simplify your representation so much, right? If you're just doing arbitrary representations, it will take more space, like you cannot compress the data. But if you're able to find some structure in the data, then you can immediately compress it. Like I take a 10 cross 10, okay, 100 cross 100 matrix, and I fill it with all ones. If you want to store it in your memory, it will take lots of space. But if you know the structure, okay, it's just one which is repeated all over. It takes hardly like maybe you can compress it to a very few number of bits, right? So this is the idea that if you can find a structure, then things become very easy. Same thing happens with us also when we are learning, right? If you look at the proofs which we have done in the previous classes, they look so complicated. But if you just do the structure, okay, you have to just apply Jensen's inequality and that's it. How easy it becomes. So that's what we are also doing, trying to find structure in our derivations, in our data, in our concepts, and then using that structure to have more powerful representation, and with very little you can do much more. Okay, the present submission is not about applications of NMF, but focuses instead on the technical aspects of finding NMF factorizations. Of course, other types of mathematical factorizations, okay, fine. So this paper is about the derivations, not about applications. Applications we'll do after this class. Here we discuss two algorithms, okay, and they are easy to implement and their convergence properties are guaranteed. We found them very useful in practical applications. Other algorithms may possibly be more efficient in overall computation time but are more difficult to implement and may not generalize to different cost functions. Okay, so they are telling different good things about their algorithms. This is how you write a paper. Unless you do it, it won't be accepted. Okay, at each iteration of our algorithms, the new value of W or H is found by multiplying. Okay, this is fine. This is what we'll find. Okay. Fine. So the algorithm is saying they improve monotonically with the application of these rules. So basically, which means you reach the local optimal, just like you do in gradient descent, right? The simplest approach is gradient descent, right? Where you update your current position in a direction which makes the result better, either maximizes the likelihood or minimizes the loss. Okay, now let's come to the stuff. So you have represented your data in terms of data vectors and stacked them up in the form of a matrix, right? Now what you have to do is, to find an approximate factorization, we first need to define the cost functions. Okay, this is important. So first you represent your data, then second you have to define a cost function. So these two steps basically are forming your space in which you are optimizing, right? Now, what cost function they are using? Euclidean distance. Simple Euclidean distance, element-wise subtraction, and then square each term and then sum over all the terms. Another useful measure is KL divergence, but since they are not assuming sum to unity, so they have formed a more generalized version of KL divergence, which is something like this: A times log A upon B minus A plus B. And they say, like the Euclidean distance, this is also lower bounded by 0. Can you prove that it is lower bounded by 0? Okay, this is a homework problem for you. You prove that this is never negative. This is always non-negative functional. And it vanishes if and only if A is equal to B. Okay. When A is equal to B, this is equal to 0, this is clear. But it cannot be called a distance because it is not symmetric in A and B. It is not symmetric. How do you make it symmetric? Huh? What is the meaning of symmetric? What's the meaning of symmetric? Yeah, D of AB should be equal to D of BA. Then it is symmetric. It is not symmetric. What will you do to make it symmetric? What do you do to make a function symmetric? Huh? Yes, you take an average of both variations. You say D of, let's say D dash of AB is equal to D of AB plus D of BA whole divided by 2. Just, okay. But they are not doing it here that way because they don't want to make it symmetric, but they want to make it analytically solvable. So they are not doing it here. It's fine. Okay. We now consider two alternative formulations of NMF as optimization problems, that is minimize V minus WH norm square or Euclidean distance with respect to W and H, subject to the constraints that W and H are both non-negative, and then again minimize the divergence function with respect to W and H, that is it. So although the functions this and this are convex in W only or H only. So these functions are convex. What is convexity? What is convexity? Yeah, but what is the use of your, why do you want your functions to be convex? Pardon? Yes, so if your function is convex, then your local minimum is same as the global minimum. So that saves a lot of headache. Why deep learning is difficult? Deep learning is difficult because it is not a convex problem. It is highly non-convex, right? There are many, many minima or maxima, whichever way you want to see it. Let's say many, many minima, and you do not know which one is the global minimum. And the algorithms which you have, which are very efficient, they can only find local minima. For example, gradient descent or whatever variations of gradient descent are there, conjugate gradient descent or so many LM algorithm or Adagrad, whatever. They all are good for finding local maxima or minima. Now, so what they are saying is in this work, so in this paper, V minus WH, if you consider W as a constant, then this is only a function of H and it is a convex function. And if you consider H as constant and optimize over W, again it is a convex function. So okay, if you consider W and H both as variables, then it is not a convex function. Then it is non-convex. That is why this is a non-convex problem. But if you do fix one, iteratively fix one, optimize other, fix the other, optimize the first one, then it becomes, at each step, it becomes a convex optimization problem. So therefore, it is unrealistic to expect an algorithm to solve problems 1 and 2 in the sense of finding global minima. However, there are many techniques from numerical optimization that can be applied to find local minima. Oh, that's what they are doing. Gradient descent is perhaps the simplest technique to implement. Okay, gradient descent is simplest, then why do we need another technique, right? But the convergence can be slow. Gradient descent converges much slower as compared to this one. I have done it, it's really slow. Other methods such as conjugate gradient descent have faster convergence, at least in the vicinity of local minima, but they are more complicated to implement than gradient descent. The convergence of gradient-based methods also have the disadvantage of being very sensitive to the choice of step size, which can be very inconvenient for large applications. You all have seen, right? Step size. If you change your step size, your function behaves weirdly. So it can diverge, or it can be very slow in converging, or it can be going in some direction which is not at all leading you towards the minimum, but towards something else. So we have seen all this. So this paper kind of reiterates those reasons. Okay, now let's come to some mathematics. So we have found the following multiplicative update rules, that they are a good compromise between speed and ease of implementation for solving problems 1 and 2. So in this method, as you have seen in KL level, in EM algorithm also, what is the hyperparameter in EM algorithm? What is the hyperparameter in EM algorithm? Huh? K, okay. K is a hyperparameter for your model. Your model, basically you decide how many latent variables you want to make, that is the K. But in the optimization algorithm itself, there are no hyperparameters, right? In the EM algorithm itself, there is no eta, no step size, nothing. Only in the model, yes, there is one hyperparameter called the number of dictionary elements or latent variables which you want to consider. Okay. So now they are giving their results, multiplicative update rules, which they are going to derive, and they write it here. The proofs of these theorems are given in the later section. Actually, we are interested in that, not in the results straight away. But what you can appreciate here is the results are so easy to implement. Just one equation or two equations, and that is it. So they are very easy to implement, and the convergence is also very good. So for both the algorithms. The first algorithm which minimizes Euclidean distance, second algorithm which minimizes the generalized KL divergence. They are very easy to implement. Okay, now I will skip this portion 5 because it's like they are comparing this rules with the additive update rules. Okay, we can skip it, no problem. Let's come to the proof of convergence, which we are actually interested in. So to prove theorems 1 and 2, which means the update rules which they have proposed, we will make use of an auxiliary function similar to that used in the EM algorithm. So actually, they are doing it in the reverse way. They are giving a solution and they are telling you that this solution is correct, but they are not telling you how to derive this solution, right? But if you read through this proof of convergence, you can read it from a different angle where you are actually trying to construct a solution. Okay, but we will do that little later. Maybe you will see that later. But now let us see what they have written, what they have presented. Okay, so they are saying they have formulated an auxiliary function called G, which is an auxiliary function for f. What was f? F was the least square error, or means the squared error, mean squared error, or simply the squared error, which means your v minus wh Euclidean distance whole square summed over all the data points. That was your f. If you differentiate it and try to find, so okay, let me, for you to be able to appreciate the problem, if I simply write f, let's say I fix my w, because in that way it will become easier problem. Let's say f of h is equal to v minus wh, w is a matrix and h is a vector, let us say, summation over, okay, let's say h, I. Okay, so if I simply differentiate it with respect to h and put it equal to 0, will that not be a good solution? Will that not be a good solution? If I simply differentiate it and put it equal to 0, will it not be analytically solvable? Yes or no? How many of you say yes, it is analytically solvable? You have done it already. Then why are you not raising your hands? It is analytically solvable. Then why don't we do it? Huh? Okay, but we can do that still. We can still do it, right? Pseudo inverse, we have seen it, this kind of problem. Least square solution we have seen. Why are we not simply using least square solution here? I'm just testing how many of you are awake. Little louder. W? It's fine. I will fix W, update H, fix H, update W, fix W, update H, and do it iteratively. How do you know that? No. Faber is okay, but Faber has compared that their algorithm with gradient descent, not with this least square solution. You missed the whole point. Go to the first slide. What is the title of today's lecture? Okay, non-negative matrix factorization. So what is non-negative here? Will your solution be non-negative? Then your solution will be negative and positive and everything basically. It will belong to real, every element will be a real number. It won't be non-negative. So this defeats your purpose. That is why this is not a good solution here. Otherwise, least square is fine, okay. Given all those problems, it works. Okay. Now, the thing is that we want non-negative solutions. So that is why we formulate an auxiliary function G such that G is always, okay, I'll show you this. This is graphically illustrated in figure 1. So this is a good representation. So this is your G. So this thing is your G, and it is always greater than F, right? Your G is always greater than F. So G is an auxiliary function, and just like we discussed, at HT, at this HT, they are same, but then you optimize over G, and you are guaranteed that you're also improving over F. And then you set this HT plus 1, go back to your F, construct another auxiliary function, optimize over that auxiliary function, you again optimize, you again improve over F. In this way, you keep going until you hit the point where G and F, basically, where the slope of G is also 0 and F is also 0. Basically, when your G cannot improve any further, and that at that point F also cannot improve any further, right? Okay, so let us see the proof they have given. What kind of auxiliary function? Okay, first is, if G is an auxiliary function, which means it satisfies this property, then prove that F is non-increasing under the update. Prove that if you improve over G, you are also improving over F. Isn't that obvious from the figure? So that is obvious. So, but they have written it in terms of some mathematical representation, which is very easy. You can go through it. Okay. So they are saying, okay, what we can see visually, they have just written it in terms of some formulas. Okay. Now, if K, okay, now they have defined the form of G. What is our G? So G is defined as F plus H minus, basically G is a function of H and HT. What is HT? HT is the current local anchor where G and F are same, and H is the variable H. So HT is the anchor, like if I go to the figure, HT is the anchor and H is the variable. So in this problem, in this one iteration, HT is fixed. So do not differentiate it with respect to HT. I was doing that. So don't do that. Do not differentiate it with respect to HT. So HT is fixed, but H is a variable. So they have formed a loss function. GH is equal to F at HT, which is fixed. So what does this remind you? This representation. F plus H minus H times derivative of F plus H minus H times something, again H minus H. Taylor series, that's what you said? Taylor series, fine, good. So this reminds you of Taylor series. And actually if you see, you can represent F in this form. F is equal to this because F is a square function of W, and if you write the Taylor series expansion, the third derivative will become 0, right? So you can write F exactly in this form. And you compare G with F, the only difference is in the second derivative, right? Now you have to prove that G is a valid auxiliary function. How do you do that? This means that you have to show that G is always greater than or equal to F, right? And G is equal to F. How do you show that? Just substitute F of HT and G of HT. So what do you get? G of HT comma HT is equal to F of HT, and other terms become 0. So you have proved already. Next is you have to show that G is always greater than F. This is the challenging part. Okay, not challenging. Okay, it is simple again. So just take a difference. Should I do the proof here? Not here. Here. Okay. Just take the difference. You have G of H comma HT. HT is fixed. Minus F of H. And you want to show that this is always greater than or equal to 0, right? To prove. right? This is what you want to prove, that your G minus F is always greater than or equal to 0. Now what you do, substitute the form. So this F minus this F is 0, this thing minus this thing is 0. Only difference is coming in K minus W transpose W. Okay, let me write down. Okay, let us put it in half the space so that I can see the equations which I need to copy. Oh, no. Okay, so what is my G? So G minus F will essentially become H minus HT transpose. This is basically K, right? And the term from F will be W transpose W times H minus HT is greater than or equal to 0. Right? I think this is what it comes out to be. Okay, this is what you have to prove. H minus HT transpose KHT, okay, KHT minus W transpose W. So this is the thing, right? Now I can substitute H minus HT with some other variable, let us say A or B, or let's say they have done it with E, nu, I think. Okay, let's say H. So basically you want to show that this they have written it in terms of nu. Let's call this as some nu transpose. This is some nu, and this thing is greater than or equal to 0. No problem. You just go to element wise thing, multiply the thing, so it becomes your nu A and B are the indices. Nu A into this K minus W transpose W into VB. You have to prove that this is greater than or equal to 0. So let us say this is my LHS, right? And now I can expand. No, summation over all AB, because so, and how can you write it? You can say my K is, if you see the formula here of K, what was K? K is delta AB W transpose W H transpose, sorry, HT A. So it means this is a vector, and the eighth index of this vector divided by the eighth index of HT. That is your KAB. It's a diagonal matrix, so A and B are always same. And if A and B are not same, then the value is 0. So this is my KAB. Let us write it. So let me write the middle term first. The middle term is, you have KAB, which is this thing, which is W transpose W H W transpose W HT A, and this element wise division HT, was it A or B? Okay, HTA, and then delta AB. And this is your K. This is your K, and you are multiplying it okay. Let me write it down separately, because it takes a long time to just go through the formula. I will post you this, or maybe we can discuss it in the next class also. I will write down the proof and then I can quickly go over it. But the main point which I wanted you to appreciate is that in this derivation, it's a very simple derivation based on a very simple principle that you form an auxiliary function which is easy to differentiate, analytically solve, and it is always greater than your actual function, and you optimize over it and you get the optima, right? So this proof is very simple, but just that copying these terms, it takes some time. I have it. I have it here, but just it takes some time. Okay, and the next maybe in the next class we can discuss this part. Yeah, it's very simple. Thank you. Assignment is due next Wednesday with a 5% penalty. If you have not submitted until now, you will lose 5% of total assignment marks. If you find any discrepancies with the data set, work with Venkatesh. Venkatesh will resolve your doubts. Thank you.
Is it deadline for today? Is it 5 p.m. or 12?
Because we always do it by the.
Actually, you didn't mention it.
Somebody asked when is it, and always we have it on before the class. No problem. Take your time. You had 2 weeks to do.
Yeah, but
I got your email. It's fine. It's fine.
actually,
Just
I
5%.
needed some time for myself, so I
No, it's
didn't
fine.
do it.
It's fine. It's fine.
Yeah. So next Wednesday means 2 days. Yeah. And 5% of assignment 5 marks, not total assignment. Yeah. Thank you.
Means the total marks of this assignment,
Yeah, assignment 5.
not the marks which you get, but the